Today, we are joined by Dr. Peter Clark. Peter is the manager of our colour laboratory. He has over 30 years experience in colour measurement sciences. He's written as well as co-authored a number of good practice guides to making reflectance and transmitted colour measurement. He's a member of the Society of Dyers and Colourists, a member of the BSI Standards Committee for the Measurement of Textiles, where he oversees all aspects of colour measurement, and also the UK representative for Division 1 of CIE, which is the International Lighting Committee. We are very proud to have him as a member of our team and excited to hear him speak today. So with that, I'm going to hand you over to Peter.
Hello. So today I'm going to be talking about edible oil colour measurement. So I'm just going to cover a few things. What is colour? What the different colour scales are that commonly used for measuring edible oil? The methods, so visual, electronic, manual, automatic, how we should be preparing our sample, and how we should be reporting our results. So start with, what is colour? So colour is three-dimensional. So what I mean by that is that we need three numbers to uniquely define a colour. So we could be saying, is it red, is it green, is it blue, is it yellow, or are we looking at the brightness, black to white? So we might use terms like hue, saturation, lightness. So what is its colour? How saturated is the colour? So how is it a really deep colour, or is it closer to white? Is it a pale colour? And then we're talking about the lightness of the colour. So is the colour is close to black, or is the colour close to white on a sort of brightness scale? Is it really jump out at you? So, so we have three things to describe our colour, and then we can uniquely describe our colour. Some colour scales you come across may have fewer than three variables. So you may have come across things like the colour of beer, the colour of whiskey, maple syrup, or things like ASTM colour, hazen. But what we're doing there is that the things that we're measuring, we know are all on the similar colours. So we've basically taken our three-dimensional colour space and we're drawing a line through colour space and saying everything I want to measure is on this line. And so when I'm looking to match my colour to this line, I'm going to assign arbitrary numbers to the line and then say, well, actually my colour that I'm measuring is closest to, say, the 0.5 or the 8. So, I'm ignoring some of the other variables there. Now, one of the edible oil colour scales is the Aocs Tintometer red yellow. This only uses the red and the yellow. So in my first diagram, where you had like the colours in the circle and then you had white and black at the top and the bottom, we're ignoring the white and the black bits. So we're really ignoring the brightness and just interested in what the colour is. And because of the way that's measured, and I will show a bit later on, we can get away with just using red and yellow. Because most of our edible oils are amber in colour, which is really a mixture of red and yellow, we can get away with just using the two colours rather than three. So how are we measuring our edible oil colour? Simply, we have some sort of light, we have some sort of optics, so we're shining white light onto our sample. Now, most of our edible oils are liquid at room temperature, and those that aren't, we tend to heat up to a higher temperature so that they melt and become liquid. In this way, we can actually shine the light through the liquid and see what colour we get at the end of it. Now to do this nicely, we're going to need something that's really nice and clear. So imagine you're looking through some sort of stained glass at the sunlight coming through from the other side. So you get this nice clear light coming through. This similar sort of concept that we have here with our edible oil. So what color scale can we use? There are a number of color scales, but the oldest one was developed by Joseph Lovibond, who founded the Tintometer Limited. And the scale actually has 4 parameters: red, yellow, blue, and neutral. Now you're going to say that's 4, and I talked about 3. Well, when we're using the Lovibond scale, we're only ever using 3 out of the 4 colors at any one time. We always report the 4th as 0. So mostly for edible oil, we're going to be red and yellow because that's the basis of the amber color of the oil. And then we're either going to be using a blue value with it or a neutral value with it. And then this is to do with how we achieve the color match. If our color is quite bright in compared to the matching that we're trying to do, we will use blue. If our color is duller than the matching, then we'll use the neutral to dull down the matching color. So in terms of an edible oil, our blue and our neutral can be sort of thought of a bit as to do with our brightness. So the Lovibond scale is originally a visual scale, and the bottom right there is a picture of the original tintometer. So you're putting different bits of coloured glass into your viewing system, and you're using reflected light up through your sample from the bottom and looking through down from the top so you can see that colour. So we don't actually have, so we're using daylight as our light source rather than having some sort of electronic lamp. So we come to the Aocs Tintometer red-yellow colour scale. It's a development of the Lovibond RYBN. Colours are similar, but they're not quite the same. Now you can see here on the field of view thing, we have 2 coloured circle dots. So the fields aren't presented together. This means that it's easier for us to ignore the brightness part of the colour match. So we can just look at the 2 dots and look at the red-yellow colour and ignore the brightness effect. If we put them close together, you'll see the brightness difference, but because they're separated with this black around them, the eye will ignore the colour difference. So in the visual instrument, the Lovibond red, yellow, blue, neutral, there are a number of coloured glass racks which make up the red, yellow, blue, and neutral. So we have the range of 0 to 70 on red and yellow and 0 to 40 on blue. Not so many blue colours in the world, so we don't need to go as far on the blue scale. And really the only edible oil that you're going to get a blue component in is something like olive oil, which has that sort of greeny colour. So you're going to need the blue to match that. And then we have the neutral. We never have more than 3 neutrals. So it's just for the colour, for the brightness balancing, we need to sometimes just add a little bit of the neutral so that we can dull down the matching colour. So generally there's 3 racks of the colours and 2 racks of the neutral in the instrument. Now, because this is a visual scale and because of the way the eye works, the scale is actually logarithmic. So when you double the colour, the eye doesn't really see double. The eye sees in a sort of logarithmic way. So when you're at the bottom end of the scale, everything's quite spread out. But as it's a logarithmic scale, as you get higher up in the amount of color that's present, the eye will contract that difference down. So if I'm talking about a perceived color difference, so the visual change from 2 yellow to 4 yellow is actually perceived by the eye as the same as the color change from 20 yellow to 50 yellow. So the higher up on the numbers that we go, we're losing resolution. So when we're doing a measurement, what we're always trying to do is to bring our color value into a more sensitive part of the measurement range. The Aocs tintometer scale is a little bit different to Lovibond because you've only got the red and the yellow. We only have a range of 0 to 40 on red. We don't go to 70, but we still have the 0 to 70 range on the yellow. Now, start having racks with equal values. These racks of the red and the yellow go up more following the logarithmic pattern. So again, it's similar to the Lovibond RYBN. We have a logarithmic scale again. It's a visual scale. And the spacing, as I said, the spacing in the racks reflects that. But there is a limitation to the Aocs scale, and that really is only good for measuring colors in the red, yellow, so the amber color space. So it's not really suitable to measure your olive oils because you haven't got that blue component. Now, some people might say to me, I've heard about this 10:1 ratio for measuring color. Well, yes, it's in the standards, but it's in the standards as a starting point for making a visual color match with a visual instrument. When you look at most common edible oils and you look at the red value compared to the yellow value, generally going to fall into a pattern where the yellow is 8 to 12 times the red value. So having a starting point on an unknown color of using a value of yellow that is about 10 times your sort of red value will get you a good way to making a good color match, but it's not a fixed definition in any of the standards that I'm going to discuss in this presentation. It's a good starting point on an unknown sample, and that's all really. So we shouldn't be fixated on having a fixed ratio of our red to yellow. It will change depending on the oil we measure, and also they're going to change a bit depending on the path length of the oil. So how should I be making my color measurement? Well, there are several defined standards from the Aocs and from ISO. Generally, the standards are divided into visual methods and automatic or electronic methods. So we have 15305 on the ISO for visual Lovibond, 27608 on the ISO for the automatic or electronic method of making Lovibond measurements. And then we have the Aocs methods 13E92 and 13J97. And these are the actually exact equivalents of the ISO method. So if you're using either of those methods, you're using the same method. And then for the Aocs tintometer red-yellow, there are two Aocs methods. There's the 13B45, the Western method, which is the visual method. And that's the one where I talked about where the racks have the different spacing in the colors in that sort of logarithmic fashion. And then there's the 13J97 for the automatic instrument. This actually is a shared method with the Lovibond RYBN. It's the same method. You're putting it in the instrument, you're making a measurement, you just got to choose the right scale on the instrument, essentially. you're doing the same thing in it. So that's why they put them together as the same method. So what is the structure of these standards? Well, they're all very similar in their structure. There's some sort of apparatus. What instrument do I need? What glass cells I need? What filtering equipment? Do I need an oven to heat my sample? And then there's something about sampling, usually a reference to some other standard. How do I take a proper sample from my barrel of oil or from what's coming out of my refinery in my refining process? How do I get a sample that's representative of the whole batch, basically? And then we have some stuff about sample preparation. How do I prepare the sample? Is it cloudy? Do I need to heat it? Do I need to filter it? And then we have the measurement procedure. How am I actually making the measurement? How many measurements am I making? Do I have more than one person make a measurement? You know, how can I be certain about what my measurement is, basically? And then we have reporting of the results. Basically, what information do I need to record so that someone else in maybe a different lab or at a different time can make the same measurement that I have made on the same sample, same oil, and get a similar result? And then a lot of the standards have a section on precision. So information on how repeatable and how reproducible your results are at different levels. So what sort of variation can I expect in my results from one measurement to another, maybe on different days and in different labs? So let's look at some of these in a little bit more detail. So if we're looking at the 15305, which is the Lovibond RYBN color, so there are references to recommended instruments. So there's the Lovibond Model F and the Lovibond Model E instruments, which are shown in the pictures there. Now, there are also recommendations on different cell path lengths for your measurement cell. So I've listed them here. So you range from 1/16 of an inch right up to 5 1/4 inch. So 133 millimeters down to 1.6 millimeters. Now you're going to be adjusting your path length depending on what your color measurement is. So again, in 15305 here, we have sampling of oil, and it refers to ISO 5555 or Aocs C147. So that's how to take my sample. So if you're not sure, refer on to the next standard. And then again, we're referring to ISO 661 in how we're going to be preparing our oil sample. Generally, it needs to be clear and bright, so we need to filter it, and we should heat it to 10 degrees above its melting point. In this way, we can be sure that we're looking through an absolutely clear sample. Now, in the visual method here, it says that we should be measuring, measurement should be done by 2 people, and the instrument should be sighted in subdued light. So we shouldn't be measuring with direct sunlight shining on the instrument, basically, because that will affect the way you see, and it just kind of interferes with the result. With 2 people measure it so that we get some sort of average. Everybody sees slightly differently visually in the way they see their color, how they perceive whether it's redness, it's yellowness. So if we have 2 people measure it, we're likely to get a reasonable estimate of what the actual color is. So we can take the average of the 2 measurements and be pretty confident in our result. So when it comes to reporting here, we should be reporting our red, yellow, blue neutral values. So in the case of an edible oil here, it's going to be a red, yellow with a blue, or red, yellow with a neutral, and the fourth value is going to be 0. But we're also going to probably want to report what our sample was, what steps we did in the preparation, did we filter it, did we heat it up, what path length we used in our measurement cell, because that's going to make a difference in what our color result is, and then maybe any other measurement conditions that might, be pertinent to the measurement. And then the lastly in the standard, there's going to be some typical repeatability and reproducibility, and these in 15305 are listed for a 5¼ inch path length. Coming now to the Aocs Tintometer red-yellow scale, so the visual. So we have the Aocs 13B45 method. This is really laid out very similarly to the ISO 15305 that we saw for Lovibond. So again, we have instruments specified. So we have the AF710 and the AF710-3 as the sort of the Lovibond instruments that are suitable for this measurement range. Now this instrument is slightly different in the fact that we're looking at our color length vertically rather than horizontally. Rather than having a long horizontal cell, we're using glass tubes. So we're just looking at the height in the tube rather than the length of the cell, but it amounts to the same thing. And this standard typically has 2 measuring marks on the tube. So it has the 5¼ inch to 133mm level, and we also have the 1 inch to 25.4mm height marked on our tube. So you fill the oil appropriately to the right level, depending on how dark your sample is. Usually dark samples, the smaller height, light samples, the longer length, so that you can actually get to color, so you can actually see some color. Again, sampling of the oil, ISO 5555 or ASCS C147. Preparing the sample exactly the same as in the Lovibond standard. We're referring to ISO 661, clear and bright, heat to 10 degrees above the melting point. Now in the visual standard here for the Ascs tintometer, there are recommended starting ratios of yellow to red for specific red values and for specific oils. So the ratio is changing as the sample gets darker. So you're going to have a different red to yellow ratio. Good place to start. May need a very slight adjustment on that just to determine whether your color of your particular oil, is matching. Again, when we come to report the results, as with the Lovibond scale, we're putting down our red-yellow values with some sort of sample identification, some sort of preparation, and our measurement conditions. Moving on to the electronic instrument version, so the automatic, so the ISO 27608 for the Lovibond RYBN. This really assumes that you have knowledge of the visual method, so the ISO 15305. So you understand how the thing works. But in the automatic reference, we have an extra step in the standards. We have a verification of the instrument performance with a reference standard added in to our measurement protocol here. So the idea of this is that we have some sort of liquid or some sort of filter of a known value that we put into the instrument so that we have confidence that the instrument is reading correctly. before we then start doing our measurements. Again, in this electronic version of the standard, we have the same glass path lengths, same list from 133 down to 1.6 millimeters. We have the same sampling, we have the same sample preparation, we have the same heating up to 10 degrees above the melting point. We have the same things about reporting our results. And then we also have repeatability and reproducibility. If you look at the repeatability and the reproducibility for the electronic methods, you'll actually find that they're smaller than for the visual methods. The electronic instruments are far more repeatable. They will give you the same answer day in, day out. You've taken out some of the human factor in there, and that's where you get some of the differences between visual methods and electronic methods, because of the way people see. Again, if we move to the Aocs scale, the red yellow, the electronic version, again, we're assuming knowledge of the visual method. And the Ascs 13J97, as I said earlier, it includes the Lovibond RYBN as well as the Aocs red yellow. Refers to Lovibond PFXI series of instruments. Again, like the Lovibond standard, the ISO 27608, we have recommended path lengths, we have verification with a reference standard. Again, you see here with the path lengths with the red yellow, there's only 133 and 25.4 millimeters. Again, sample clear and bright, heat to 10 degrees above the melting point, reporting the results so that somebody else can replicate them. And again, typical repeatability and reproducibility. Okay, now it's time for some questions for you. We're going to put up a little poll. I think Carl's going to introduce that.
Thank you, Peter. Okay, so I'm going to go ahead and launch our poll. We just want to see from the people participating today what their normal practice are for sample preparation. It's a 3-part question. If you'd like to participate, that would be great. I will give everyone a minute or two to fill in the poll, and then we'll have a look at the results. Okay, we'll just give it another minute just to make sure everyone has had a chance. Okay, Another couple of seconds and then we'll end the poll. Okay, so let's have a little look at the results. So are you heating your sample before analysis? 48% of you are. Are you filtering your samples before analysis? We've got quite a mixed result there with pretty equal between yes and no. And what path length sample cells do you use to analyze your sample? With most people are using 5 1/4 inch. So thank you for participating in the poll. I'm going to pass you back to Peter. Peter, have you got any comments on the poll?
Yes, it's good to see that a lot of you are bothering to heat your samples, because that can be quite important and interesting on your path lengths. I'm going to be talking about a lot of these points in the next few slides, but good to see that some of you are actually using different path lengths depending on what you're measuring, and you're not sticking with the 5 1/4 or the 1 inch. So let's have a look then at our sample preparation. If our sample is solid or semi-liquid, we're going to be needing to heat it. So in the bottom left picture, I have a palm oil. So I have it in its solid state. I have it in a sort of semi-liquid. You can see that it hasn't fully melted, and that actually looking through it, it's cloudy. And then I have it in its fully melted state. So we're aiming to heat it 10 degrees above the melting or the cloud point, so that we're certain that what we're seeing is a nice clear sample. Now, having a nice clear sample doesn't always tell us the whole picture. You may need to do a little bit of experimenting to find the right temperature to heat your sample, especially if you've got a palm oil. I will come back to that in a minute. Having said that about heating, we're going to want to avoid overheating. So overheating some may scorch or discolor it. Probably need to be most careful about this if you're using a microwave to heat your sample up. You're going to need to determine yourself with your particular microwave how many seconds is going to give you the right sort of temperature you're looking at for your oil. Another effect that we might see is in the right-hand picture I have there, where you can see that the sample's clear, but I've got some sort of structure. So this is caused by the sort of unevenness of the temperature distribution within your sample. So what we would recommend there is that we stir our sample. So we get just a glass stirring rod, move it up and down in the cell just before we take our measurement. So we're going to stir it, even up the temperature, even up the structure, so we have a nice homogeneous structure. And then we'll probably wait 2 or 3 seconds for once you've taken the stirring rod out, for everything to sort of settle down, and then take our measurement. So coming back to the palm oil is a little bit different from a lot of the other oils in the fact that it has multi-fractions of oil. So we can actually get a situation where the shorter chain fractions will melt first, and then the longer chain fractions won't have melted, but visually you may not see that. So you may need to actually heat it a little bit hotter to be able to see that effect. So these graphs illustrate here. If I'm on the left here, I have a blue measurement at 40 degrees. Now, if I'm getting blue, usually an indication on something like a palm oil that there's it's turbid, it's cloudy. So heating it a little bit more, so in this case, heating it to 50 degrees gets rid of that blue component. So we need to heat it hotter if we see a blue value on a palm oil, because we should only be seeing a red yellow because it's amber in color. Moving over to our sort of red and yellow graphs there, you can see generally heating it to 50 degrees has brought the color down, so we've got a nice clear sample, but a couple of those samples have got longer chain fractions in them. And you actually see that when you heat that hotter to 60, 70, 80 degrees, you see that drop in color because you've finally melted those longer fractions. So depending on your refining process, if you're in a refinery, you may need to heat your sample a little bit hotter than you originally think, looking at it visually. You may need to do some experiments just to heat it a little bit hotter and see if the color values reduce because you've heated it a little bit hotter. And then you'll know that is the temperature that you should be making your measurement at. So once we've got our sample hot, we may find that actually we have some other problems. We have maybe had some turbidity in the sample, or there's some stuff that we need to filter out. Especially important when you're using your automatic method or your electronic instrument, because the electronic instrument is going to interpret turbidity, cloudiness as extra color, because basically what's happening is you're scattering light sideways and it's not reaching the detector. So you need a nice clear sample for that light beam to come straight through, not get deflected, so that the detector will see it. In a visual instrument, you may get away with it a bit more because the human eye can filter out things. If you've got measuring cottonseed oil and you've got seeds floating in the oil, your eye is going to ignore that if it sees that in the field of view, but the electronic instrument doesn't know to ignore it. It will include that in its measurement. So you need to do some sort of filtering if your sample is cloudy. Now, coming to path length, you can see in the picture on the right there, the longer my path length, the more color I'm going to see. So if I've got a very pale color I'm trying to measure, to get more color into my measurement so that I can actually determine what it is, I want to measure it in a long path length. So I want to be measuring probably at the 5 1/4 inch length. If my sample is very dark, so I'm looking at maybe a crude or a semi-refined oil, so halfway through my refining process, I'm going to be wanting to look at a shorter path length so that my color is not too saturated. Otherwise, I'm going to read 70 yellow and not really know how dark it is because I've reached the top limit of my instrument. So let's have a look at a sample here. What we're trying to aim for on the Lovibond color scale is that the total of my color units, so my red, yellow, blue, and neutral values, should really add up to something a bit less than 20. So if I'm getting really dark values, I want to be reducing that color. As I said at the beginning, color scales are logarithmic, so the eye is seeing logarithmic. So if I've got a very long path length and I'm up at the sort of 40, 45, 50 level on my yellow reading, my resolution is not good. Someone else coming to do a measurement might actually grade my sample at 30 or 70. I don't, I have quite what seems like a big color difference, but it isn't. As I said earlier, the perceived colour difference between 2 and 4 yellow is about the same as between 20 and 50 yellow. So if we want to get a better resolution on our sample, we want to reduce the path length. So if it's too dark, we reduce the path length. So here we reduce that in a 1-inch cell down to about 12 yellow here. Much better, we can get much more closer measurement between different people because the eye variation is less. Also on our measurement cell, one of the most important things for an automatic instrument is that our cell should be clean. And more important to have actually the outside clean because we need a nice smooth air to glass interface. Any liquid on the outside is going to deflect our light beam. And also going to scatter the light in all sorts of directions. So we could get funny light effects happening with light bouncing inside our instrument. If we're heating something up, we should be using a borosilicate glass. These are similar to like your Pyrex jug that you might use in your kitchen. So they can take the heat. You can pour hot oil into them and they won't shatter on you. Typically in these instruments, the recommended fill height is about 3/4 full. So not too full that you can't lift it and put it in the instrument, but not too empty that the light beam is going to cut through the top surface. So looking at our instrumentation, you have visual, you have Tintometer Model E and the Model F for your RYBN scale. You have the Lovibond AF710-2 and the 710-3 for our Aocs scale. And then for the automatic, we can choose from the latest version, the Lovibond Model FX, or if you've got a slightly older instrument, we've probably got a Lovibond PFX I series, or even a Lovibond PFX series. So these are the ones that are recommended in the standards. And only the Lovibond instruments have the full RYBN scale in them if you're using that scale. We also need to look at the environment we're operating in. Is our instrument clean? Is there dirt and grease on the inside? Is the window glass in our automatic instrument dirty? Have we got dirt and grease on the filters and the racks? All of these are going to add colour to our measurement. So we're actually going to read differently to what we think we're reading. And when we're going to get an inaccurate colour measurement. So in our visual instrument, dirt on the racks is going to increase our colour measurement. Discoloration of the white reference inside, we're going to get a different colour. Light source, again, if the lamps have aged, we're going to get a different colour. So we really want to keep an instrument clean and not leave spillages inside them. So, most issues that we come across are going to be due to poor sample preparation or poor choice of our path length. So we might be choosing too short a path length, too long a path length, depending on whether our sample is dark or light. We should also be measuring according to the instrument instructions. Now, if we go to an electronic instrument, the manufacturer will have put in their instructions how we should do any zero or baseline measurement. That might be with the lid open, say, it might be with the lid shut, might be with something in there, might not be. Generally, with a Lovibond instrument, when we're doing a baseline, we're going to have an empty sample chamber, so no cell in there. We're having a lid shut, and then we're making our baseline measurement. We can validate the way our instrument is measuring, so we can use a reference liquid. Ideally, you want to be looking at something that's a similar value to the type of sample that you're measuring, so that you know that in that particular instrument measurement range, your instrument is performing well. So your reference filter, it could be a filter. Liquids are generally better because they're going to test your sample preparation in that as well. So you're going to test whether your cell is nice and clean, whether you've put it in the correct position. So if we get a good result with our validation liquid or our validation filter, we then have confidence that our instrument is measuring correctly. So if we have any issues, then the issues are going to be with our sample. They're not going to be with the instrument. So it's going to be things like we haven't heated the sample hot enough. The sample might need filtering. A sample cell may be dirty. Or we're just using the wrong path length for the particular sample. So as I said here, we're near our instrument, we're going to measure according to the instructions, use the appropriate scale. So with the electronic instruments, generally you can pick on the menu whether you're using the Lovibond RYBN or the Aocs red yellow. We need to make sure we're doing the zero measurements correctly. We need to make sure that we're putting the measurement sample in the correct position. In a PFXI series, usually pushing the sample to the far right. In a Model FX, pushing the sample to the back. And then simply you're shutting the lid, making a measurement, and noting the values. So as I said before, we can come back to the Lovibond and the visual measurement. So we've got our two fields of view close to each other. And so we're using the major two colors to make our color match. So we're looking at the red yellow in the case of most edible oils to get our color close. And then we're going to need to use the third color. So we're either going to be using the blue or the neutral to adjust that brightness. So where our color is brighter than the matched color, we're going to be adding the blue to our red yellow to dull our sample down so that the two will come into the same brightness. If our sample is duller than the match color, we're going to be adding the neutral. Now the neutral is added not to our sample but to the match color, so it dulls down that matched color so that we can equalize the two brightnesses. Now once we've equalized the brightnesses, we're going to then need to maybe adjust the color, our red yellow value slightly so that they match at the new brightness. It's far easier to match two colors properly if they're of the same brightness. So we may need to sort of go around the loop a few times here for our visual color match. So in a visual instrument, we'll then add up the amount of red, yellow, blue, and neutral and write that down as our result. Now, similarly here with the Ascs method, because the colors are separated, as I said earlier, you're kind of ignoring the brightness, so you're just using the red and yellow. So in some ways, a little bit more of a simpler measurement than the Lovibond RYBN. So you're just matching the red and yellow to the closest. So the automatic instruments, they would do all that process for you. So you choose the appropriate scale. So in case here of measuring the Lovibond, we're going to pick the Lovibond RYBN, set our path length with an empty chamber, make our zero baseline, put our sample in, measure it, and read the results off the display. We don't have to move colours in and out, much simpler to do. Very similar with the Ascs, with the automatic instrument. We're putting our sample in, we're doing our baseline, pressing the result, and we're reading it off the scale. And then we come to reporting our result here. So basically what we're doing is recording everything relevant so that somebody else can replicate our measurement. So when your supplier or your customer gives you a measurement result, or you give them a measurement result, they should have all the information needed to be able to replicate that. So they should know about what heating you did, what filtration you did, what you thought about the sample, what your measurement temperature was, what method you were using. So important to communicate which scale you've used for the measurement, because that can cause confusion otherwise. And if you've only given someone red yellow values for Lovibond because you've forgotten to give them the blue and the neutral, they might actually assume that you were using the Aocs scale. So really need to give everybody all the information needed. So optical path length, instrument use, color scale, measurement values, and anything else that you or your customer have agreed, or you've agreed with your supplier that you need to know about the oil. So you might think, wow, what a lot of stuff to remember. Well, we've made it easy. We have our edible oil methods book. So we have specific methods for specific scales and instrument types, and we've got step-by-step instructions, recommended conditions, how to prepare our sample, how to report our results, all in a very simple step-by-step guide. So, questions?
Okay, so we have now reached the question and answer section of our webinar. We've had a number of questions come in. So first one I have for you, Peter. What does the N value in a Lovibond scale tell us regarding our sample? I have never measured an N value in any of my samples.
Okay, so the N value, as I just talked about, we're talking about, this is a neutral. So what we're doing with the N value is when we're looking, probably best to think of it in the visual instrument. When I'm looking at my two fields of view, I have my sample and the color I'm matching. Now I think in my first step with I've got my red and yellow, I think they're roughly the same color, but my sample is actually darker than the match color, although I think they're roughly the same color. So my neutral value is actually dulling down my match color. So I'm trying to make my match color the same brightness as my actual sample so that I can get a better color match, because in a Lovibond system, if you've got the brightness the same, then it's far easier to get the color matching correct. So what I'm doing is I'm adding the neutral to dull down my match color so I can then see the two colors that I think are the same, at the same brightness, and then I'll probably find that they're slightly different, so I'm going to tweak my match color slightly compared to my sample color so that I can then say, yes, I like that color. So neutrals, they're really to help you get that color match accurate.
Okay, thank you, Peter. Our next question. Does it matter what size opening filter is used to filter samples?
That's really going to depend on how cloudy a lot of your samples are. Generally, I think the sampling standard talks about a 45 micron filter or filter paper as a good size to filter out. Generally, if you're using that sort of size, you're going to get a good clear oil that you'll then be able to make a good color measurement with.
Okay, thank you. Do you have to use the verification standard every time you use the machine? How often do you need to verify?
Right. To some extent, how often you want to verify is going to depend really on how many measurements you're making. Typically, when you turn your instrument on, you're going to leave it to warm up, say for 20 minutes. And then you want to know that your instrument's performing well. So I would generally be warming my instrument up, doing some sort of verification check with my filter or my liquid. I'll probably be doing that at the beginning of my shift or the beginning of the day or just before I'm doing a whole series of measurements. Once I'm happy with the performance of my instrument, I probably don't need to do that again until, half a day later. So maybe if I've done it in the morning, I might want to do it again after lunch. Really depends how your lab's running. If your lab's running 24/7 and you've got lots of samples, and you want to be sure that you haven't made a mistake or there's eliminate instrument issues, you might want to do it a bit longer. So if you're doing several samples an hour, you might decide that I want to verify every couple of hours. But generally, if you're only going to do a few, probably, beginning of the day, and then after about 4 or 5 hours, do it again.
Okay, thank you.